Today we're going to spend 2 days on this topic because these problems can get tricky, but they have all basically the same setup. So we're going to do some basic ones today and some trickier ones on Monday. So suppose you have a drinking cup in the shape of a cone. As you pour water into the cup, the volume of water in the cup is changing. So is the height of the water in the cup, and so is the radius of the circle where at the water level. Okay, so you have all different variables changing as we pour water into this cup. So in this section, we're going to solve problems where several variables are changing at the same time. And our main task is to relate these rates to each other. So that's why they're called related rates problems. So on the first page of this packet, we have a worked out example. And then we'll come back and do some new examples. But the first page of this packet has a worked out related rates problem. And you are allowed to use this as a reference sheet when we take a quiz on related rates next week and on your test. So on the left are some general guidelines, and on the right is an example doing the general guidelines. All right, so in general, a related rates problem is one where you're trying to find a rate of change. Okay? And the situation involves different rates of change that are related to each other. So for example, we have a 6-meter ladder leaning up against a wall. If somebody stands at the bottom and pulls it away at a constant rate of a ½ meter per second, we want to know how fast the top of the ladder is sliding down the wall when it reaches the 5 meters up the wall mark. All right, so step 1 is going to be read the problem. As with all problem solving, spending some time understanding the situation and what's really being said is worthwhile. And so we're thinking about this picture, and our intuition says that the ladder is initially going to fall slowly. It's initially just going to start slipping down the wall a little bit, right? And then as the wall is providing less resistance to the ladder because it's being pulled further away, it's going to fall faster and faster. All right, so step 2, carefully define the variables in the problem. So these are calculus problems, and thus they're dynamic. So we have rates of change are going to be some of our variables, and we use notation to represent rate of change, like dr d theta or dy dx to represent rates of change. Be clear on which quantities can change and which quantities are constant. Okay, so step 2 in our example, we've got a picture. Right? This is the wall and the ground and the ladder, 6-foot ladder. If we let x be the distance between the bottom of the ladder and the wall, and y will be the vertical distance up the wall, the length of the ladder is constant. That doesn't change. But as I pull the bottom of the ladder away, x and y are both going to be changing. So even though we were looking at a single snapshot in time, when the top of the ladder is at 5 feet above the ground, the distance must be a variable in the problem because the ladder is moving. Okay, so the ladder is moving, and we're interested in something that happens at a specific snapshot in time, but we can't make that vertical distance constant because that is not constant for all time. All right, so step 3, always draw a picture, put your variables in it. Helps you wrap your mind around what's happening in this problem. Okay, step 4 is determine and symbolize what is given to you. Okay, so we know that dx dt, they told us that they are moving the bottom of the ladder away from the wall at a rate of 1/2 meter per second. So dx dt, that's the rate of change with x with respect to time, is 1/2 meter per second. And then 5, determine and symbolize what you're being asked to find, what you want to know. We want to know dy dt, right? I want to know the rate at which the top of the ladder is moving when y is 5. Should add that in there. Because the top of that ladder is going to be moving at different rates at different times. All right, so we've got two important variables here, x and y, right? And in that picture, we want to come up with some equation that relates the important variables. So we might use the Pythagorean theorem, x squared plus y squared equals 6 squared in that picture. Once you have an equation that relates your important variables, implicitly differentiate it. Take d dt of both sides. It's been a while since we've done that, so you got to think back. D dt of both sides. And in this case, we're going to end up with the derivative of x squared is 2x times dx dt. And the derivative of y squared is 2y times dy dt. And the derivative of 6 squared is 0. So when we did implicit differentiation before, we were taking d dx of both sides. So when you were taking a derivative of an x, it was just plain old derivative rules. But now my independent variable is t. So for both of them, you have to multiply by dx dt or dy dt, because x is really a function of time, right? And y, the horizontal distance, is really a function of time. So if you want to take the derivative of either of these, you have to multiply by the derivative of the inside, which is dx dt. All right, so then redraw your picture for the specific time that they asked us to look at. So in our case, we wanted to substitute in a y equals 5, when the height is 5 is what we're interested in. So now I draw my picture where I put in a 5. I use the Pythagorean theorem to get the x is 3.3166. This is my snapshot in time. Okay. Then, once you have your picture for the snapshot, plug in the values for the variables and the rates that you know. Plug in the stuff that you know. So in my implicit formula, that was 2x dx dt plus 2y dy dt equals 0. Now we plug in all the stuff that we know for the snapshot in time. X is 3.3166, so I have 2 times x. Dx dt I know is constant, a half. 2 times y, which is 5, times dy dt, which is what I was asked to find, right? The rate of change of y with respect to time. Then you just solve for dy dt, and we end up with that. That would be the rate of change of the top of the ladder when the top of the ladder is 5 meters up. And it came out negative because the top of that ladder is moving down, right? So our rate of change is negative. Okay, we're going to come back to this in a little bit, but we're going to do another problem first. All right, so we have a boat pulled into a dock through a pulley that's 20 feet higher than the bow of the boat. The rope is pulled in at a rate of 2 feet per second. How fast is the boat approaching the dock when there's 30 feet of rope out? All right, so I have to draw a picture. I can't possibly start trying to solve this until I have a visual of what's happening. So let's see, we've got a dock. Right, there's a dock here. My picture of a dock. Okay. And there's a pulley 20 feet higher than the bow of the boat. So there's some kind of like pulley mechanism above the dock attached to my boat that's pulling the boat in. So a boat is pulled into a dock through a pulley 20 feet higher than the bow of the boat. So this has to be 20 feet. And the rope is being pulled in at 2 feet per second. How fast is the boat approaching the dock? So variables that are changing would be this. We'll call that R for rope. And then we'll call this horizontal distance X. So both of those things are changing. So I didn't put in, they're asking me about the moment when there's 30 feet of rope, but I can't put that in the picture yet because that is a changing quantity. So I'm going to leave it as a variable for now. Okay, so is there, let's see, what do I know? And what do I want? Now that I have a picture of what's happening, what do I know? $20 is fixed. Yep, good. X prime is 2. The rope is pulled in at a rate. So yeah, and I'm going to call it drdt instead of r prime, just to remind us that t is the variable, the independent variable here. Now, that is being pulled in, right, at a rate of 2 meters per second, so it's -2, because that distance is getting shorter. So if the quantity r is decreasing, dr dt should be negative. All right, so I know dr dt is -2 always. It's a constant rate, right? And what do I want to know? I want to know dx dt. I want to know how fast that is, the rate of change of the quantity x, how fast the boat is coming into the dock. Dx dt when r equals 30 is what I'm interested in. All right, is there some equation that can relate my important variables in this picture? Yes, x squared plus 20 squared equals r squared. Just the Pythagorean theorem. Again, it's not always the Pythagorean theorem, but 2 pictures now where that has been the relationship between my related variables. Okay, let's implicitly differentiate this. I'm going to take d dt of both sides. So if I'm taking the derivative with respect to t, and I want to take the derivative of x squared, take the derivative of the outside function, that would be 2x, and then the derivative of the inside function, and the inside function is an x, and its derivative would be dx dt. And d dt of 400 is 0. d dt of r squared, if that said d dr of r squared, it would just be 2r, right? But because it's d dt, it's 2r times the derivative of the inside function. My inside function is r, so it would be dr dt. Now I plug in stuff about my snapshot in time. Not until you've done this do you plug in stuff about your snapshot in time. So let's draw a picture of the snapshot. This is 20. My r is 30. So that means that this distance x the boat is from the dock would be, I have to do it on my calculator. It's not a Pythagorean triple. Okay, so it would be 30 squared minus 20 squared square rooted. About 22.36 feet. Okay, so there's my snapshot in time. Now plug all the stuff you know into this implicitly differentiated equation. So x is 22.36. dx dt is what I've been asked to find. That's what I want. So that's going to stay my variable. And r in this case is 30. And dr dt I know is a constant -2. That was what was given. And then I just solved this equation for dx dt. So that's -120 divided by 2 times 22.36. -2.68. Does it make sense that that came out negative? Yeah, because if you look at our original picture, the boat is moving towards the dock, so x is getting smaller, x is decreasing, that distance is decreasing, so its rate of change should be negative. And my units here on dx dt should be feet per second. Units on x is feet, units on time is seconds. So that's one thing you have to be careful about, is checking that they don't give you some of the given information in different units, like hours and seconds. If they do, you just have to convert it all to one thing. Okay, let's do another one. We have water flowing into a cone. The cone has a height of 16 and the radius of the top of the cone is 4 centimeters. Okay, water is flowing in at a rate of 2 cubic centimeters per minute. How fast is the water level rising when the water is 5, 10, 15 centimeters deep? Actually, was there a second part to that boat question? Oh, how about when there is 22 feet of rope out? We didn't answer that part. That's okay. All right, we're going to work on the 5. So water's flowing into a cone. So I got to draw myself a picture. I'm going to make a cone. The best advice I can give you is to draw big pictures. Make them real big so that you can put in all the detail and not get lost. Okay, so there's my cone. It has a height of 16 centimeters. So there's the top of my cone. 16 centimeters. All right, and it has a radius at the top of 4 centimeters. Okay, and water is pouring in, right? Water is going into this cone. All right, so let's see, what do I know? And what do I want? All right, what rate am I given here? The flow of water. What variable represents the rate of flow of water? The derivative of something, yes, because it's a rate, so it's got to be a derivative of the volume of water in the cone, right? So they're giving me, this is cubic centimeters per minute. That's a rate of change of a volume, right? You can tell by the units. So what I know is dV dt. Its volume of water in the cone is changing at 2 cubic centimeters per minute. And it's positive because the volume of water in the cone is increasing because water is flowing in. So that's positive. I know dV dt. What do I want to know? dH dt. Where should I haven't drawn an H in this picture. Where should I put it? Right, so the H is going to represent the height of the water in my cone. So I'm going to just draw a water level kind of at a random spot here. And I'm going to call this H, the water level of the water in the cone we'll call H. So I would like to know dH dt, the height of the water when H is 5. Let's just start with the 5. Okay, so I have some important quantities here, V and H. Can I relate my important quantities in this picture somehow? Let's call this guy R. We don't know what that is. The volume of a cone would be what? Yeah, something. I can't remember either. Let's look it up. Okay, volume of a cone is 1/3 pi r squared h. But r is not one of my important variables. Like my important variables come from the stuff I know and the stuff I want, right? So v is important and h is important. I've got an extra variable in my equation there, r. So what I'd like to do is have volume as just a function of h. Can I relate them somehow? Let me give you a hint. What's that shape I just outlined? A triangle. What's that shape I just outlined? A similar triangle, similar to the little purple one. Okay, so similar triangles, their sides are in proportion. So I could say h is to, what's the height of the full cone? 16. So I could say h is to 16 as r is to what? 4. And then I could solve for r in terms of h so that I'd only have one variable over here. Because they didn't tell me anything about how r is changing. So I can't use r in this equation because I just don't know anything about it. So I'm going to try to put in an h because h is what I want to know about. All right, so 4h equals 16r. Solve for r, and I get 1/4 h. So then I come over here and replace my r. Volume is 1/3 times pi times 1/16 h squared times h. And then I could simplify that. Volume is 16 times 3 is what, 48? Yeah, 48. So this is h cubed times pi over 48. All right, now I have a nice equation that relates my important variables, volume and height of the water. Now I implicitly differentiate. And I'm out of room, I need a new page. Volume is pi over 48 times h cubed. So now I take d dt of both sides. So here I get dv dt. Derivative of v with respect to t is just dv dt. And then d dt of pi over 48 times h cubed. I'm going to use my power rule on h, and I get pi over 16 times h squared. Brought the 3 down in front, and then I reduced that fraction, times dh dt. Okay, now let's think about my snapshot. Okay, so what do they want to know? dh dt when h is 5, right? So now I'm going to draw a picture here where h is 5. Okay, so could I figure out the radius when h is 5? Yeah, but do I need to? Right, I just need to know, do I need to know the volume? dv dt is constant, so I'm just going to plug in the stuff I know, right? dv dt is constant, h is 5, and I'm solving for dh dt. So I don't even actually have to get anything else from this picture. dv dt was what? 2? 2? Pi over 16 times 5 squared times dh dt, which is what I'm looking for. And then I just solve for dh dt. So I divide both sides by 25. And then multiply both sides by 16 over pi. So this is 32 over 25 pi. And let's get an approximate value for that. Make sure it makes sense. .407. And my units on h is centimeters. My units on time, minutes. About a little less than half a centimeter per minute. That makes sense. At least it's positive, which is good because the height is supposed to be increasing. Okay, we can check our answer with this geometer sketchpad thing. Here's my cone-shaped tank, right? Water's flowing in. So I'm going to fill the tank. So you can see that as the tank fills, the height gets higher, the radius gets bigger. And the height is changing faster near the bottom, and it slows down as we get towards the top. Okay. So let's show dh dt. Here's my formula, my function for dh dt, and fill. And we're looking for height to be 5, so I'm just going to hit this here. There we go. dh dt is 0.407, which is exactly what we got. All right, one more. Given the ladder and the wall situation from the guideline on the first page, what is the rate at which the angle the ladder makes with the floor? What is the rate that angle is changing when the bottom of the ladder is 3 meters from the wall? Okay, so I have a 6-meter ladder, right? And now they're asking about the angle that the ladder makes with the floor. So we'll call that theta. When the bottom of the ladder is 3 meters from the wall. So this is x. That's the other variable that they're asking me about. And so now let's write down what we're given and what we want. Okay, so what I'm given here is the same thing I was given in the last ladder problem, that this rate of change, they're pulling the bottom of this ladder away. So dx dt is 1/2 meter per, can't remember, second. And this time, they want to know the rate of change of the angle. So they want to know d theta dt when the bottom of the ladder is 3 meters from the wall, when x is 3. All right, what equation could I write that will relate my two important variables of theta and x? Cosine theta. The cosine of theta is adjacent over hypotenuse. Then I take d dt of both sides. Okay, so the derivative of cosine theta is negative sine theta. But since theta is a function of t, we have to also multiply by the derivative of the inside, d theta dt. Okay, and then d dt of 1/6 x would be 1/6. But then you also have to multiply by dx dt. Chain rule. Then we're going to plug in our snapshot. Okay, so they want to know when x is 3, we're looking for d theta dt, and I need to know what theta is. So could I figure out what this angle theta is when x is 3? Inverse cosine. Yeah, I know that the cosine of theta would be 3/6 or 1/2. I could take the inverse cosine of 1/2. And what angle has its cosine of 1/2? 60, yeah. Or pi/3, because that's how we do calculus, right? Radians. And what is the sine? Well, I'm just going to write it down first. So I have negative sine pi/3 times d theta dt, which is what they asked me about, so I don't know it yet, equals 1/6 times dx dt, which was given as 1/2. All right, what's the sine of pi/3? Yeah, it's positive. Positive what? Oh, oh no. SIN, yeah. √3/2, yeah. So this is going to be negative √3/2 because of this negative out front. Times d theta dt equals 1/12. And then just solve for d theta dt. So it would be 1/12 times 2/√3, which would be -1/6√3. And if I wanted, I could rationalize that denominator, but I don't care because I'm just going to get a decimal anyway. negative 1 over 6 radical 3. And I get negative 0.096. Okay, so let's think about the units. What are my units on theta? Radians. We're measuring in calculus, you measure angles in radians. So this is 0.096 radians, and my units on time were seconds. So this is negative 0.096 radians per second. Does it make sense that that came out negative? That the rate of change of theta is negative? Yeah, as the ladder moves away, that angle is getting smaller, which means its theta is decreasing, so its rate of change should be negative. Okay, so your homework is mostly from the scanned related rates problems. Where's they're there. Okay, so I want you to start that homework now.